Okay, guys, so let's continue. So last time we went over the introductory portion of chapter 10, that is the 1 and 2 sampling test of hypothesis. And today we are going to cover article 4.10.4 and 10.5. Okay, guys, so let's see over here. First of all, let me let you know that what we are going to do here in this section. So we formally consider test of hypothesis on the single population mean and then after the two population mean. So that's what we are going to do. 10.4 is single population, 10.5 is two population. So test of single mean, that is given over here. You can see here test of single mean. So that here you can see H0 that is equal to, I told you last time, H0 is nothing but your null hypothesis and H1 is nothing but your alternative hypothesis. So null hypothesis always relates with the mean. So whatever the mean value can, that means I mean to say that is with the equality. So nu is equal to nu 0. And if you have alternative hypothesis just on the left side of your normal curve, right side or left side, if it is left side, you can say nu is or H1 and nu value is less than nu 0. If it is right tail, you can say nu is greater than nu 0. If it is both sided, in that case, you can say nu is not equal to nu 0. So that's how you can consider. We are going to do that thing also, that how to fix your, how to consider your H0 and H1. First of all, we are going to see the same thing, single sample test concerning the single mean, in which the variance is given to us. That means sigma value is given to us. So if you read this part, you will come to know this thing. The model for the underlying situation centers around the experiments with x1, x2 up to xn representing the random sample variable, random samples from the distribution with the mean nu and the variance sigma square. So sigma square is variance is given to us. And we can consider like this: the appropriate test statistics should be based on the random variable x. As I told you, x1, x2, xn, that is x bar. And last chapter, we have seen the central limit theorem, which essentially states that despite the distribution of x, the random samples x bar has approximately a normal distribution with mean nu and the variance sigma square divided by n, or you can say sigma divided by square root of n. And for a reasonably large sample size. So nu remains the same, nu x bar equal to nu and sigma x bar, that is equal to sigma x bar square is nothing but sigma square by n by central limit theorem. We know this thing. So the z value is nothing but z is equal to x bar minus nu over sigma, sigma over square root of n. So this is a standard normal variable z, standard normal random variable z. And you know this thing that probability of negative z alpha by 2 is less than z is less than z positive z alpha by 2, and that is equal to 1 minus alpha, because this is a normal curve and both the sides left and right tail, that is this alpha by 2, this alpha by 2. The middle area is simply 1 minus alpha. I'll show you this thing too. So that is 1 minus alpha. And if you plug this value of z over here, that is x bar minus nu, or nu equal to nu 0. So nu 0 over sigma over square root of n, and try to make this one as a function of x bar. So if you try to make this one as a function of x bar, that means you need to multiply throughout by sigma over square root of n here, here, and here. So here it will get cancelled out, and then after add nu 0 throughout. So this will get cancelled out, and nu 0 minus z alpha by 2 is less than x bar is less than nu 0 plus z alpha by 2 and sigma over square root of n, both the sides, of course. And this left hand side I would like to denote by some a, and right hand side I would like to denote by b. So my x bar lies between some small number a and b. So that is nothing but the interval of confidence. So that is called the interval of confidence, and that is also known as the test procedure for a single mean variance known. So that's what is mentioned here. You can see here the test procedure for a single mean, the variance known, that is z greater than or equal to z alpha by 2 and z less than negative z alpha by 2. That means your z values lies between this interval, and that is, again, I told you that whenever your z value lies between this negative z alpha by 2 and z alpha by 2, do not reject H0. So whatever the z value or mean value is provided to us, or once you find the probability or whatever it may be, and that lies between, suppose, negative z alpha by 2 and positive z alpha by 2, and that interval, if it lies in this one, don't reject H0. We are going to see this thing in the example too. If it lies outside this interval, always you reject H0. Do not reject H0 means you are rejecting other way around, I would say H1. And if your Z value is lying outside this interval, in that case, you have to reject H0. That means you are accepting H1. Okay, guys. So that is the things. Do not reject H0, and do not reject means rejection of, do not reject H0. Rejection of H0, of course, implies acceptance of the alternative hypothesis nu is not equal to nu 0, which with this definition of the critical region, it should be clear that there will be probability alpha rejecting H0 when indeed H nu is equal to nu 0. And of course, we can write the same critical region in terms of the computed average X bar. So rejection of H0, if your X bar, computed value of X bar is less than A is this part. A, as I told you, A was nothing but once you write this one as a function of X bar, whatever the left side is there, that is your A and this is your B. So if your A, you can see over here, if my X bar is less than even A, right, my lower interval, B is the upper interval. So if X bar is less than A, you have to reject H0, or if it is outside the interval, X bar is less than A means it is outside lower interval. X bar is greater than B means it's outside upper interval. You can see over lower and upper interval, right? And that's what I mean, that alpha by 2 and alpha by 2, two-tailed. So this alpha by 2 is alpha, total probability is 1. So it is 1 minus alpha, that is the middle portion. Okay, 1 minus alpha is your middle portion. So test of one-sided hypothesis, that is simply like this, nu is strictly greater than nu 0. As I told you, that is the one-sided hypothesis on mean involve the same statistics described in two-sided case. The difference is this one. And it could be less than 2. So single mean favors H1 comes from large value of Z, and thus rejection of H0 results when the computed Z is greater than Z alpha. And obviously the alternative hypothesis H1 nu is less than nu 0. The critical region is entirely in the lower tail, right? Critical region, this is critical region entirely on the upper tail. For nu less than nu 0, critical region is entirely in the lower tail, and thus rejection results from Z less than negative Z alpha, right? So one-sided testing case, the null hypothesis can be written as nu is less than, equality is always there, right? You know this thing as I told you. Okay, so let's go for this example. This example says that a random sample of 100 recorded death in the United States during the past year shown an average lifespan 71.8. See, nu equal to 71, average lifespan is 71.8 years. Assuming the population standard deviation 8.9 years, sigma is given to us. Does this seem to indicate that the mean lifespan today is greater than 70? Don't consider this one. This is now 70. So this is your mean value, right? So mean equal to 70 and greater than 70, that is your H1, just one-sided tail. So critical region, my alpha is nothing but, you can see level of significance is given to us, that is 0.0 alpha, 0.05. Excuse me. Sorry. Allergy. Yes, so alpha equal to 0.05. Alpha equal to 0.05, that means naturally I can find, I think I need to solve this example for you guys, right? So let me stop sharing this book and let's go for the book exam. What we say? Let's go for the whiteboard. Okay, so example 10.3 says that, example 10.3. As I told you that your H0 is nothing but nu equal to 70 years, and my H1 is nothing but nu is, let me write double, nu is greater than 70 years. That's the demand of the question, and my level of significance alpha equal to 0.05. 0.05, that means I have to go like this. 1 minus alpha is equal to 0.95, because 0.1 minus 0. That is 0.95, or you can write 0.950, because sigma is given, and sigma value is, what is the sigma value? Sigma is given to us, and that is 8.9 years. So sigma is equal to 8.9 years. And because sigma is given, that means we have to go for z-score, and z-score, that means table A3 in the back of, on the back of the book. So table A3, and if you find this one with this 0.905 on table A3, 0.905 or 0.950 or 00, that will lie somewhere over here in the table. So just try to match this number, and whatever you're getting here and here, try to add this one. You're going to get that is equal to, here you're going to get 1.6, and here you're going to get 1.5 and 1.6. So this 0.9500, that lies between 0.5 and 0.6, actually 0.5 and 0.06, right? So because I think 0.04 and 0.5, it lies between 0.04 and 0.05, and that's why I would like to consider the common part. So this corresponds to 1.6 and 45, 1.645. And because here I consider just alpha, because I have, you can see over here, it is strictly greater than H1 is strictly greater than 70. That means we are looking for only one-sided region, and this is your alpha's level of significance is given to you. So don't divide by 2. Whenever you're two-sided tail, in that case, only we divide by 2. So alpha by 2. Otherwise, just stay with alpha. If it is left tail, again, just stay with alpha. So my critical region is now nothing but z is equal to, what is my z value? So z is equal to, yes please, x bar minus nu 0, or nu divided by sigma over square root of n, and x bar minus nu and sigma over square root of n. X bar is nothing but, what is my x bar? X bar is also given to us. X bar is equal to, in the problem, it is 71.8 years, right? 71.8 years. Lifespan. Okay, so I can write 71.8 years minus nu is nothing but my 70, and sigma is given to us 8.9, and divided by square root of n, that is equal to 100. If you use your calculator, you're going to get that is equal to 2.02. That is equal to 2.02. So this is your z value, and whatever the critical region we found over here, this is actually nothing but your z alpha. This is your z alpha. So z alpha is equal to 1.645. Z alpha is equal to 1.645, right? And z value is 2.02. So this is 1.645, and whatever z value you are getting over here, that is equal to, that is outside 2.02, right? So naturally, I can say, if you want to go for, so naturally we can say that we do not support or we reject H0, because my z value, you can see here, z is greater than z alpha, implies reject H0. Or suppose you are asked to do the same thing using probability. In that case, you have to find the probability. So what is the probability, guys? Probability of z greater than 2.02. 2.02, that is equal to 1 minus probability of z less than 2.02. And again, if you use table A3, you can see here 2, you can get it from here, 2.0, and 0.2 you are going to get here. So what, this is the value, and that value is nothing but, you again, when subtract from 1, you will be getting 0.0217. You can see, guys, here my probability is extremely low. So it's too low. My probability is extremely low. Because my probability is extremely low, that means whatever we have considered, that is not true. Means my H0, whatever null hypothesis I have considered, that is not true. So this implies that H0 do not support or reject H0, or you can say reject H0, right? So I can say that we reject H0 reject H0 through probability, because you can see probability is too low, right? Probability is too low. If your value, Z value is lying, if you are looking up based on Z value, then Z value must lie somewhere over here, from here to here. In that case, you are not supposed to reject H0. But if Z value is crossing this line, if Z value is crossing this Z alpha, right, 645, 1.645, Z value is crossing this line, in that case, you have to reject H0. So you can say that as a result, we can reject as a result, we can reject H0 in the favor of H1, right, is even stronger than suggested by 0.005 level of significance. So as a result, the evidence in favor of H1, right, in favor of H1 is even stronger than that of, or that suggested by 0.05 level of significance. So that's how you can solve the example. Now let's go for the next example. So let me save this file, and then after we can go for the next one. Okay, guys. So now let me erase this part, all drawings, and let's stop sharing this one, and let's go again to the book. So my book again says that example 10.4. Now, this is the two-sided tail now. A manufacturer of sports equipment has developed a new synthetic fishing line that the country claims has a mean braking strength of 8 kilograms with a standard deviation 0.5 kilograms. There's the hypothesis that nu equal to 8 kilograms. See, null hypothesis nu equal to 8 kilograms clearly mentioned over here. Against the alternative hypothesis, nu is not equal to. In the examination, this will not be provided to us. You have to figure it out, this thing. Nu is not equal to 8 kilograms if the random sample of 50 lines is tested and founded to have a mean braking strength of 7.8 kilograms. And 0.01 level of significance you need to use over here. In the previous example, it was given a level of significance 0.05. That is equivalent to say that 95% of the confidence interval. Here it says 0.01 level of significance. It is equivalent to say that 99% of the confidence interval, because you know this thing that alpha equal to 0.01. So that is 1 minus alpha is nothing but 0.099, and that is equal to 99%. So it's a 99% of the confidence interval. So it's the same thing. Just guys, if somebody uses the different language, don't get confused. So that's the example, and now I would like to answer this question again just by using the two-tail problem. So let me again stop sharing this one, and let's go for the whiteboard. So in this example, it says that example number 10.4. So first of all, H0 is nothing but nu is equal to 8 kilogram. So H1 is nothing but nu is not equal to 8 kilogram. Okay, level of significance alpha is equal to 0.01. So alpha equal to 0.01, and you can see over here because they are not equal, so it's two-sided tail. So here it is nothing but alpha by 2. Here is nothing but alpha by 2. Alpha by 2 and alpha by 2 is alpha. So this region is 1 minus alpha. So alpha is equal to this one. So naturally 1 minus alpha equal to 0, 1 minus 0.01, and that is equal to 0.99. So 99% of the confidence interval, you can say 99% of the confidence interval you can say. or level of significance is 0.99. Sounds good. Same thing. Okay. Now, as I told you that you have to have, here I started like this, right? Like this, but here it is two-sided. So what I'm going to do 0.01, that is alpha. So naturally, this implies that alpha by 2 is equal to 0.01 divided by 2, so 0.005. Once you have 0.005, 1 minus 0.005, and that is equal to 0.995. And this 0.995 that you need to, again, sigma is given, so you need to use table A3. And if you use table A3, you're going to get one value, and that value is 2.575. 2.75, you know how to use table, so I'm not going for the same thing again and again. So this is nothing but negative 2.575, and here it is nothing but positive 2.575. Positive 2.575. That means if my z value lies between this interval, that means I'm going to accept H0. If z value is lying outside this interval, that means I'm going to, outside these numbers, I'm going to reject this one, right? Or other way around, if my probability is too low. So let me now start like this. Suppose, first of all, I'm going to find my z. So z is nothing but x bar minus nu, or nu 0 divided by sigma over square root of n. We are given sigma is nothing but, what is the sigma over here? Sigma is equal to, okay, line 50 is given, so it is 0.5. So sigma is nothing but, sigma is equal to 0.5 given to you, and n is equal to 50. Okay, guys, n equal to 50, and we are given x bar is equal to, what is my x bar? My x bar is nothing but, if you, okay, in the last line it is mentioned, 50 lines is tested and found to have the mean breaking strength 7.8 kilograms. So x bar is equal to 7.8 kilograms. So let me use these numbers over here. So 7.8 minus nu 0 is nothing but 8 divided by sigma is equal to 0.5 divided by square root of 50. And if you use your calculator, you have to get over here negative 2.83. So negative 2.83. At this stage, you can come to the conclusion, depending on the nature of the example in which it is, which form it is asked for. So it is negative 2.83 and negative 2.80, that is somewhere over here, negative 2.83. So naturally, this implies that reject H0. Reject H0, right? You can come to this conclusion. But suppose somebody says that, no, I would like to go through the probability. Sounds good. So, but up to here, we can, of course, come to the conclusion. So it says that since the test term in this example is two-tailed and desired p-value is twice the area of the shaded region, twice the area of the shaded region, right, to the left of negative 2.83, and therefore table A3, we can go for probability of. Now it is two-sided, right? Two-sided, that means I'm not going to write simply z, but I'm going to write absolute value of z, and that is greater than or equal to 2.83. That is greater than 2.83, either way, right? And because they are same, both the sides, that means I'm going to multiply it by 2 because same area is there, both sides. So probability, or 2 times probability of, now I will write simply z, and less than negative 2.83. You can write directly also. Again, use table A3, and you're going to get that is equal to 2 times, and this one, whatever you are going to get, that will give you 0.0046. Again, you can see probability is too low probability, right? Probability, because to have your probability, suppose you have this is 0.5 and more than 0.5, that is the valid probability, and less than this is 0. This is 0. Somewhere over here, suppose it is 1. So 1 is the maximum probability, this is the minimum probability. 0.004, you can see that is 0.0046, extremely nearer to 0, means even there is minimum, very minimum chance of occurring that event. So naturally, that's not going to happen. And that's why we can reject H0, or I can say that which allows us to reject the null hypothesis, so which allows us to reject the null hypothesis that nu is equal to 8 kg, 8 kilogram at the level of significance smaller than at the level of significance smaller than 0.01. And that is the answer. Right, guys? That is the answer. And now relationship to confidence interval and estimation. Let me save this file, and then after again we can go for go to the book. So let's stop this one and let's start sharing the book again. So my next example or next part says that relationship to confidence interval estimation. So readers should realize by now that the hypothesis testing approach to statistical inference in this chapter is very closely related with the last chapter, that is chapter number 9, in which we have seen the confidence interval approach. Confidence interval estimation involves computation of the bounds within which it is reasonable for the parameter in questions to lie. Right, and for the case of the single population mean nu and sigma square known, the structure of both hypothesis testing and the confidence interval estimation is based on the random variable z equal to this one, right? So same part of things, z equal negative z alpha by 2, z alpha by 2, and like this. Alpha is a level of significance that computing 101 minus alpha % confidence interval on nu and rejecting h0 if nu 0 is outside the confidence interval, right? If your new value is outside the confidence interval, and if nu 0 is inside the confidence interval, as I told you, don't reject h0. Hypothesis is not, null hypothesis is not rejected, right? It says the hypothesis means null hypothesis is not rejected. The evidence is very intuitive and quite simple to illustrate, and that's fine. Good. So here it says that the evidence of confidence interval estimation to hypothesis testing extends to differences between two means, variances, ratios of variances, and so on. As a result, the student or statistics should not consider confidence interval estimation and hypothesis testing as separate form of the statistical inference. Both are same thing, just different way of looking at the scenario. Otherwise, both are same thing. Okay, and now we are going to solve the example. We are going to see the part in which the variance is not given, because always we do like this. That's what we did in the last chapter also. First of all, we went over the known variance and then after unknown variance. And that's what we are going to do over here. And then after we are going to repeat the same process for two samples, right? So test of single samples, variance unknown. Now variance unknown, in that case, we will be given the sample variance, and we are going to work because sample variance small s will be provided to us. Variance is not given. That means you cannot think about the z-score, but you have to go through the chi-square distribution, and chi-square distribution is nothing but the, you can say the way around t distribution. So always whenever the variance is not given, always we rely on chi-square distribution. I mean to say t distribution. Okay, then that's what it says over here. The random variable x1, x2 up to xn represent the random sample from the normal distribution with the unknown sigma square, nu and sigma square, and then the random variable, it is x bar minus nu divided by sig s over square root of n. Just consider like this. Take this square root of n over here, s divided by square root of n. That makes the perfect form. As a student t distribution with n minus 1 degree of freedom, right? Because whenever your t distribution at that time, you have whatever n sample size just reduced by 1, and you will be having the n minus 1 degree of freedom, and that's what we are using to look at table A4. That is based on t distribution, n minus 1 degree of freedom, and the structure of the test is identical to that for the case of sigma unknown, with the exceptional that the value sigma in the test statistics is replaced by the computed estimates s, and the standard normal deviation or standard normal distribution is replaced by t distribution, as I told you. So everything is same, only t distribution, sigma is replaced by s, and that exceeds. You can see that h0 you can reject if your h0 is not lying in the interval negative t alpha by 2 n minus 1 to t alpha by 2 n minus 1. So same thing, that the probability of negative t alpha is less than t alpha, plug the value. That's what we did in chapter 9. Just plug the value and you're going to get the confidence interval. Right? You are going to get the confidence interval. If you want, I can show it to you, but actually it is not required. Okay, let me show it to you, and then after I can move to example number 10.5. But before that, I just want you to read this example. Always keep in mind this thing, just like our previous case, this is not equal to two-sided tail, but it should be one-sided tail, right tail or left tail too. And that's what mentions over here for h1 nu greater than or equal to nu 0, reject results when your t value is lying outside the right interval, and nu less than nu zero, the critical region is given by t less than your lower interval, negative t alpha n minus 1. Okay, fine. Sounds good. So now read this example, and then I will explain to you this portion, and then we will solve the example. Okay, fine. The Edison Electric Institute has published figures on the number of kilowatt hours used annually by various home appliances. It is claimed that vacuum cleaners uses have average of 46 kilowatt hours per year. Average 46 kilowatts per year, that is your new value, per year. If a random sample of 12 homes, your n equal to 12, included in a plant study indicates that vacuum cleaners uses an average 42 kilowatts per year, that is your new value, right? I mean to say new zero value, right? X bar minus new zero. So 46 is your new value because that's the average value. Average 42 kilowatt per hour with a standard deviation 11.9. That is your standard sample deviation, small s hours. Does this suggest at the 0.5 level of significance that the vacuum cleaners use on average less than 46 kilowatts per hour annually? See, it's less than 46 hours, means that is your new one equal to new less than 46 is your H1. New less than 46, that is your H1, and equal to, that is your H0. Okay, assume the population of kilowatt hours to be normally distributed. Okay, guys, so let me help you to solve this one. I will explain to you the confidence interval first, and then after we'll solve this example. You have all this data, so I'm going to repeat this data for you too. So let me again go to my whiteboard. So let's go to the whiteboard. Okay, guys, already I think I saved this file, but let me just make sure this thing, let me clear all the drawing, and now again I can go for this one. Okay, as I told you that if you want to go for the confidence interval, my t was nothing but x bar minus nu zero divided by s over square root of n, and my probability is negative t alpha by 2 is less than t alpha by 2, and that is equal to 1 minus alpha. So naturally, if I plug the value over here, I don't want this, actually this one, but anyway, probability of, so let me write negative of t alpha by 2, negative of t, so negative of t alpha by 2 is less than t is nothing but x bar minus nu, or you can say nu zero, divided by x bar minus nu zero divided by, yes please, s over square root of n, and that is equal to t alpha by 2. Let me multiply throughout by s over square root of n, and let me multiply throughout by s over square root of n, and that is equal to 1 minus alpha. So this will get cancelled out, right? And as I told you, just like your previous case, so there is, this implies that my p is equal to nu zero minus t alpha by 2 s over square root of n is less than x bar is less than nu zero plus t alpha by 2 s over square root of n, and that is equal to 1 minus alpha. So this is the thing but my a, or you can say this is the thing but by me. So this is my interval a to b, you can say. So if it lies inside the interval, that means H0 is accepted. If it lies outside, so here accept. If it lies outside, that means here it is H1 is accepted. So accept H1, that means reject H0. Reject H0. So that is the meaning over here. And now I would like to go for example number 10.5. Example 10.5, we read the data. So let me start like this, that H0 is nothing but nu is equal to 46 kilowatt, right? Kilowatt per hour, 46 kilowatt hours. And my H1 is nothing but nu is greater than 46 kilowatt hour, right? Level of significance alpha equal to 0.05 is given to us, 0.05 alpha. So naturally, and my n is equal to 12. So v is equal to 12 minus 1, that is equal to 11. So v is equal to 11. That means if you go for your table A4, table A4, what I'm going to get? V equal to 11, you can, these V values are given here. So V equal to 11, that is somewhere over here. And you are given V equal to 11, and you are given with alpha equal to 0.05, right? Alpha equal to 0, because it is strictly, is it less than or greater than? I think it is less than, right? My bad. So new less than. Okay, so the alpha equal to 0. This alpha value, this is your V value is here down, and alpha value they are like this. So alpha equal to 0.05 somewhere over here. So just try to match this value, whatever the value you're going to get, that is your T value. So here your T alpha is nothing but T alpha is approximately negative 1.796. Negative 1.796. Okay, guys, sounds good. So it is here's negative 1.796. That is your T alpha. That is your T alpha. And now I'm going to find my T is equal to X bar minus nu divided by S over square root of n. So X bar is nothing but, what is my X bar, guys? Help me. My X bar is nothing but 42, right? That is given to us. X bar is equal to sample standard deviation. Sorry, X bar, that is nothing but 42, and you are given sample standard deviation, and that is nothing but 11.9. So S is equal to 11.9. So let me plug the values over here. Here it is 12 minus, sorry, it is 42. So it is 42 minus 46. Always keep in mind this thing, your X bar must be very close to either side of your new value. And S is nothing but 11.9, and divided by square root of n equal to 12. So that is equal to negative 1.16. And you can see this is negative 1.7 and negative 1.6. That is somewhere over here. This is my negative 1.16. Negative 1.16, right? Because my negative 1.6 that lies. See here, it is less than, but now this is critical region is this one. This is my critical region. Critical region, but my value, my T value that lies on the other side, safe part, that means do not reject H0. So do not reject H0. Right? Other way around, suppose somebody says that I want to go for the probability. Okay, fine. So probability is nothing but P is nothing but probability of, yes, T. Don't write C, please. T less than negative 1.16. Right? T less than negative 1.16. So negative 1.16, that will be, again, use table A4, and you're going to get that is equal to 0.135. Now again, 0.13, this is my probability 0, minimum probability 1, 0.135. See, 0.5 is somewhere over here, 0.5, but 0.1 is here, 0.1, 0.2, and this is 0.2, 0.3, 0.4. So 0.1 between 0, so this is 0.135. Again, my probability is too low, so I would say 0.135, right? 0.135. I think I need to verify this one. Whenever my probability, because 0.135, that is actually is not that reasonable answer. If you have 0.135, I think it is 0.435. Okay, so 0.435, that is very somewhere over here, and that's why you can say that do not reject H0, because that's reasonably good probability. So I would say, okay, so good probability. If it is 0.001 or something like that, but if it is at least 0.23, some chances are there, 0.3, 0.4. Yeah, people sometimes say that 0.5 and greater than 0.5 is a good probability, but at least here we are looking for at least some chances. So if you have 0.23, something like that, I think that is also a good probability. It should not be 0.001, 0.0. It should not be between 0.0 and 0.1. But if it is 0.1 and higher, at least some chances are there. Okay, so I will say that do not reject H0, right? And conclude that the average number of kilowatt hours used annually by home vacuum cleaner is not significantly less than 46. It will not be significantly less than 46, right? That's what you need to conclude. So conclusion, as I told you, I don't want to write everything. So do not reject H0. And you can conclude that the average number of kilowatt hours, the average number of kilowatt hours used annually by the home vacuum cleaner, let me write another abbreviation, is not significantly less than 46, right? Or you can say not significantly less than 46 kilowatt per hour. So that's how you can solve the examples based on this one. Let me save this file again. And let's go for the next article. And next article is nothing but, let me clear my drawing and stop sharing this one. Exactly the same thing we are going to repeat for the two samples. So my two samples are nothing but two samples, taste of two means. Two samples and taste of two means. Okay, guys. So two independent random samples of size. Now you have two samples. That means suppose two companies. You are comparing two companies, production of one company, production with another company, something like that. So whenever you have this type of situation, that means you have two means, two n values, two number of samples, two standard deviation. If standard deviation is known to us, if standard deviation is not known to us, in that case, you will be a samples standard deviation, that is S1, S2 will be provided to us. So everything that is in double. So we are going to get this thing in the form of Z equal to X1 minus X1 bar minus X2 bar. As I told you, two sample means nu1 minus nu2 and standard deviation sigma 1 square over n1 sigma n square over n2. If now, guys, look at over here, it could be possible sometimes this standard deviation. Now you have two standard deviation, but both the standard deviations are same. It could be possible, right? So if you have the same standard deviation, you can take sigma 1 square equal to sigma and sigma 2 square equal to sigma. Because you have sigma and sigma common over here in the numerator, take it out. So sigma 1 square, sigma square and sigma square outside simply sigma, you will be having this one, this estimation. And your H0 in this case will be nu1 minus nu2, and you have some error over there, that is D0, because as I told you, nu1 and nu2, this mostly they will be different. So you will be getting one number over here. So nu1 minus nu2, that is equal to H0. And if you want to fix your H1, if it is right tail, in that case, nu1 is greater than nu2. If it is left tail, it will be nu1 is less than nu2, or nu1 is not equal to nu2 if both the tails are there, right? So because my Z value is like this X1 bar minus X2 bar minus D0, nu1 minus nu divided by sigma 1 square over n1 in general, suppose sigma 1 and sigma rho, they are not same. In that case, again, it will lie probability of Z negative alpha by 2 is less than Z alpha by 2, and that is always 1 minus alpha, right? Normal curve, Z alpha by 2 will be removed. So in between it is 1 minus alpha. Okay, so you can plug that value again, and you can find the confidence interval. All these things are already done so many times, so I don't want to repeat the same thing, but you can find the confidence interval over here. So that is for known sigmas in both the cases, for both samples. Now we have unknown. I talked to you about both the things, that known sigma and same, and known sigma and same, and known sigma, known variances, but they are not same. Now, again, the same kind of scenario will be there for unknown sigma. We don't know the standard deviation, but it could be possible that they are same, right? Or they are different. So unknown, but equal variances. So sigma 1 and sigma 2, they are sigma 2, that is equal to sigma, right? But because it is unknown, and that's why we have to rely on chi-square distribution, T distribution. So again, same thing, and T is given by X bar minus X2 bar, but because they are same, so just like your previous case here, because they are same, I can pull this one out, S1 and S2 equal to S, or SP you can say. So here it is SP, here it is SP, just a symbol, and you can take this SP out. So that's why you are going to get, instead of sigma, you will be getting SP over here. Otherwise, and here it is capital T. So otherwise, it remains the same. Look at here. Capital T equal to x1 minus x bar d0 and SP and this one, right? This SP square is actually given by this one, SP square, because SP square that based on your sample standard distribution, standard deviation, sample standard distribution, and n1 minus both the sample sizes. So that's why you can write like this. And this n1 plus n2 minus 2, that is the degree of freedom. So V is nothing but n1 plus n2 minus 2, somewhere over here. I think it is mentioned over here. So we can reject H0 at significance level alpha when the computed T statistics that exceeds. So once you have whatever the confidence interval you have, if your T value, this T value, whatever you're going to find from the table A4, if T value lies outside this one, outside your lower bound or outside your upper bound, in that case, you can reject H0. But if T value lies inside your confidence interval, in that case, don't reject H0, accept H0. Okay, fine. So let's go for, and the same thing can be done for mu1 greater than mu2 and mu1 less than mu2, right? In greater than mu2, if it is inside the region, critical region is outside, greater than, right tail means outside, right? If it is inside, don't reject H, do not reject H0. If it is outside, reject H0. Same way, suppose lower bound is there and mu1 is less than mu2. In that case, suppose your T value is lying, below the lower bound. In that case, reject H0. If T value is lying on the other side of the lower bound, then don't reject H0. Let me take this example, and I think idea will be more clear. So let me go through this 1-2 examples, and then after, again, we'll try to solve some examples, exercise problems. It says that the experiment was performed to compare the abrasive wear of two different laminated materials. 12 pieces of material, see, 12 pieces of material 1 means N1 equal to 12 is provided to us, were tested by exposing each piece to a machine measuring wear. 10 pieces of material 2, N2 equal to 10, were similarly tested. In each case, the depth of wear was observed. The samples of material 1 gave an average coded wear of 85 units. Look at over here. Now it is given to you x1 bar is equal to 85 units with the sample standard deviation, right? Sigma 1 that is equal to, given to you, sigma 1 equal to 4. While the samples of material 2 gave an average of 81, x2 bar equal to 81 with the sample standard deviation that is equal to 5. That means my, so x1 bar, x1 bar, x1 bar, it is unknown. So x1 bar is nothing but where I was. The samples of material 1 gave an average wear of 85 units, x1 bar equal to 85 with the sample standard deviation. So S1 equal to 4, while the samples of material 2 gave an average of 82, means x2 bar equal to 82 with the sample standard deviation of 5, means S2 equal to 5. Okay. Can we conclude that 0.05 level of confidence of interval or level of significance that the abrasive wear of material 1 exceeds that of nu1 is exceed of material 2 by more 2 units. So nu1 is greater than nu2 by more 2 units, so plus 2. So nu1 is greater than nu2 plus 2, like this. That's the meaning. Assuming the population to be approximately normally distributed with equal variances. Look at over here, equal variance means you are given unknown variance, guys, unknown but equal variance. Okay, so that's what we are going to do now. So just pay attention here, guys. Let me stop sharing and let me go for the book. Let's go for, sorry, the whiteboard. So example 10.6 says that 10.6 says that nu1 and nu2 represent the population mean of the abrasive wear of material 1 and material 2 is respectively, and I have my H0 is nothing but nu1 minus nu2, and that is equal to 2, right? And H1 is equal to nu1 minus nu2 is equal to 2, or otherwise I told you that H1 is nothing but nu1 is greater than nu2 and plus 2 more units. Same thing. And my alpha is equal to 0.05 level of confidence. And as I told you, V is nothing but I have given N1 equal to 12 and I am given N2 is equal to 10. So my V is nothing but N1 plus N2 minus 2, and that is equal to 12 plus 10 minus 2, and that is equal to 20. So V is equal to 20. Now it is one-sided tail, alpha equal to 0.05. So just use table A4, and table A4 that gives you something like this. Here your alpha value and here you have V value. So V is equal to, you have 20, and just go in the same line, and alpha value 0.05. Make this value, and whatever you are going to get over here, that value is nothing but, guess what? That value is V is equal to, that value T is critical value, right? So now T is equal to, or T alpha I would say, T alpha, or T alpha is greater than, okay, so T alpha by 2. But actually it is not required, right? So we can say T alpha or T 0.05. That is equal to T 0.05. And that is equal to 1.725 for V is equal to 20. This 1.725 will get V equal to 20, right? V equal to 20. As I told you, my X1 bar, that is nothing but 85, X2 bar is nothing but 81, my S1 is nothing but 4, and S2 is nothing but 5, N1, N2 already I mentioned over here. Sounds good. And now I have to use my SP formula. My SP is, or SP square is mentioned. So I can write SP square, that is equal to S1 square n minus 1 plus S2 square n minus 2 divided by N1 plus N2 minus 2. And if you plug the values, you're going to get some value over here. Take the square root. So this implies that your SP, let me take the liberty to write it down, 4.478. SP value is 4.478. Why I need SP value? Because because my T distribution, and therefore my T distribution is nothing but X1 bar minus X2 bar minus D0 divided by, it is given like this, right? SP and square root of SP times, actually. Write this SP separately. Don't try to mix up the things, okay? So it is SP and then square root of 1 over N1 plus 1 over N2. And that is equal to, that is equal to, so here it is 85 minus 81, and this is new 1 minus new 0, and new 1 minus new 0 is equal to, not new 1 minus new 2 equal to 2. So that is equal to 2, because D0 is nothing but new 1 minus new 2, and that is equal to 2. Divided by my SP, that is equal to 4.478, and square root of 1 over 12 plus 1 over 10. And if you use your table, you're going to get the 1.04. You're going to get 1.04, right? So T value is lying on 1.04, right? Now T alpha was, look at over here, T alpha was, if you have this normal distribution, and this is my T alpha. So T alpha was 1.725, and your T value, whatever you are getting over here, that is 1.04. So 1.04, that lies somewhere over here, right? This is 1 point, this is suppose 1 somewhere over here. It is 0, and so here 1.04. 1, but so that lies on the other side, right? It's not lying in the critical region. This is your critical region. So it's not lying over here, it's lying other side. And that's why I would say that do not reject H0. So here you can say that do not reject H0. Or other way around, you can say you can accepting H1. Or if you want to go for probability, then probability of T greater than what? What is the probability? This T alpha, T, right? So 1.04. And that is equal to 1 minus probability of T less than 1.04. And if you count this probability, you will get that is equal to 0.16, right? 0.16. And because 0.16, you heard just now in the last example, I told you that 0.16, your minimum probability is 0, maximum probability is 1. But suppose you have, this is 0.01, then 0.02 dot dot dot. So 0.16 that lies somewhere over here, 0.16. If it is 0.001, something like over here, at that time we don't, but at least it is 0.1 and so on, 0.1 and so on, except H0, right? So because there are some, of course it's very low, but some chances of getting that event to be happened. So that's why we can say that that is equal to, do not reject H0, and we are unable to conclude that the abrasive wear of material 1 exceeds that of material 2 by more than 2 units, right? So do not reject H0, and we are, you can say like this, we are unable to conclude that the abrasive wear of material 1 exceeds that of material 2 by more than 2 units, right? So that is your answer. That is. And the last part is left out, and last part says that now the unknown but the equal variances. Let me just save this file. Whenever you have unknown and unequal variances, at that time, only thing is your V, degree of freedom, because unknown means naturally T distribution, chi-square distribution, but degree of freedom in the known SP or S1 and S2 known, and they are equal. I mean to say unknown variances, but they are equal. In that case, my degree of freedom V was just N1 plus N2 minus 2. It was quite simple. But whenever the situation is different, I mean to say that unknown variances and they are not equal. They are not equal. In that case, your V is quite difficult. You get over here S1 square by N1 plus S2 square by N2 and then whole square divided by S1 square by N1 whole square divided by N1 minus 1 plus S2 square by N1 whole square divided by N2 minus 1. This is a tedious formula. All this formula I given on page number 350 of this book in the next, I think in the same chapter, yeah, page number 350. We will not go over there, but page number 350, all this formula are given and whole table is given. So just try to use this table for your chapter 8, 9, and 10. Okay, guys, and just because we want to distinguish this one, and that's why I would like to write this one as T dash x1 minus x2 minus d0 nu1 minus nu2 and s1 square n by n2 and s2 square by n2. And this s1 square, s2 square, that is okay because the s1 and s2 that will be provided to us, degree of freedom that is given like this, and t negative alpha by 2v is less than t dash is less than t alpha by 2. Just plug this value over here and try to make this one x1 minus x2. So you are again going to get one confidence interval. Anyway, guys, that's fine. So he has not given any example over here based on this unknown variance and not equal unknown variance, but that's fine. Now I just would like to go over a few of the examples from your exercise. Page number 350, as I told you, that whole table is given. Let me just show it to you, probably helpful to you, and then after just allow me to take some examples. Look at this. This is the table. Whole table is given to you. Please take the printout so that you can use this one as per your convenience. And then let me just go down, because rest of the articles, they are okay because of the limitation of time. I think it's not possible to go over all the articles, but let me just stop over here and come to say in terms of articles, right? This is our last article for this course, and let's go examples, at least two or three examples. These are some examples here. So let me start with example 10.19. So let's go over at least some of the examples, not all, but at least some of the examples. So example 10.19 says that in a research report, Richard H. Weindruch of the UCLA, University of California, Los Angeles, medical school claims that mice with an average lifespan of 32 months will have to be about 40 months old when 40% of the calories in are replaced by vitamin and protein. Is there any reason to believe that nu is less than 40 if 64 mice that are placed on this diet have an average life of 38 months with a standard deviation 5.8 months? So standard deviation is given to us. Use p-value in your, now use p-value. You have to go for the probability to conclude your result, right? Okay, guys, so just read this one twice. All the numbers are given to us. X1 equal to X1. Let me let you know X1 bar equal to 38 over here. N1 equal to, sorry, N equal to 64. Sigma is 5.8, right? Sigma is 5.8 and my new value is 40, right? New value is 40. So it is simple. It is simple. Let me stop sharing this one and let's go for the book. So, sorry, let's go for the whiteboard. So example 10.19, as I told you, my X bar is nothing but 38. My N is nothing but 64 in the example. Sigma is nothing but 5.8 and my nu is nothing but 40. I would like to write my H0, nu is equal to 40 months, nu equal to 40 months, and H1, my nu is less than 40 months, right? That's what it says. And now I would like to go for my Z score. So Z is nothing but X bar minus nu divided by sigma square root of N. And that is equal to 38 minus nu is equal to 40 divided by 5.8 square root of N is nothing but 64. And that is equal to negative 2.76. Negative 2.76. So if I go for, of course, it says p-value, right? So negative, one can go like this also, z value. So you can use table A3 and level of significance is given to us or not? Level of significance is not given. Look at over here, guys. So that means we don't have any other choice because you cannot form the, right? So that's why confidence interval you cannot form. So you have one has to rely on the probability value. Fine, sounds good. So let's do like this. So my p-value, P is equal to probability of Z less than negative 2.76. And if you go to table A3, negative 2.73, that corresponds to 0.0029. Right now, 0.029, you know this thing, this is my 0 and this is 1, this is my 0 and this is my 0.1, 0.0029, that lies somewhere over here. So it's extremely low probability. So I would say too low, and that's why it's too low, and that's why reject H0. Reject H0, right? So reject H0. So I think, yes, we are good with this one. Okay. So let me save this part, and now again let me stop sharing this one and let's go for the another example of the book. Another example says that example number 20 is just similar way. I would like to go for different. So 21. So 10.21. An electrical firm manufacturer light bulbs that have a lifetime that is approximately normally distributed with a mean 800 hours and the standard deviation 40 hours. Test the hypothesis that nu is not equal, nu equal to 8. Oh, it's already given 800 hours against the alternative, and nu is not equal to 800 hours if the random sample of 30 bulbs has an average life of 788 hours. Use p-value in your answer. See again, confidence level is not provided to us. And this type of example is really good to ask in the exam. Anyway, guys, so again, just look at this example and let me share my whiteboard. So here my whiteboard says that example number 10.21. Okay, 10.21 here I'm given my new value is equal to 800, my sigma is equal to 40 hours, and then after my X bar is nothing but 788, and I have my H0 is nothing but nu is equal to, nu is equal to 800, right? And each one, of course, it is given to you in this example. So that is really, really good for you. This one, so naturally I can go for z is equal to x bar minus nu over sigma over square root of n, and that is equal to 788 minus 800, and my sigma value, what was, it's only, I wrote it down, 40. So 40 divided by square root of n is nothing but, what is my n in this example, guys? 30, right? So n is equal to 30. Let me write down here. So n equal to 30, and if you use your calculator, okay, 788 minus 800 divided by 40 and square root of 30, and you are getting that is equal to negative 1.64, negative 1.64. So naturally my p value, now look at here, guys, it is equality. That means you have alpha by 2 over here, and you have alpha by 2 over here. So, and this is 1 minus alpha, right? So it is both side. So p value is nothing but, probability value is nothing but p of absolute value of z greater than 1.64, and that is equal to 2 times probability of z less than negative 1.64. We did one of the examples like this. That is equal to 2 times 1.64 with my table. 1.64, and that is 0.0505, and that is equal to 0.1010, right? 0.1010. So that means hence the and the mean is not significantly different from 800 for alpha is equal to, yes, 0.101, right? This is actually your alpha value. So because that's a probability, so I can say that hence the mean is not significantly different from 800 for alpha less than 0.101, right? 0.101. And that's why do not reject your H0. So mean is not significantly different, right? So do not reject H0 or 0.1, as I told you that this is 0 and this is 1, 0.1 is somewhere over here, 1 and something, 0.1 that is over here. So do not reject H0. Do not reject H0. Okay, guys, let's go for another example. So let me just save this part and let's go for, stop sharing this one, and let's go for the book one more time. And this time I would like to go for what? I think, yeah, in example 10.23, sigma is unknown. If you can read the example, it says that the test of hypothesis that the average content of containers of a particular lubricant is 10 liters if the content of a random sample of 10 containers are 0.10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, liters. Use 0.01 level of confidence, level of significance, and assume that the distribution of the contents is normal. Now, guys, you are not given the data like X bar like this, but you are given some random data which comes from some practical information, right? That's what usually happens. So we need to find our X bar, our sample distribution, right? Sample variance, I mean to say. So we need to find all these things. So read this example twice and keep these data in mind. And let me just use these data to solve this example. Nice example, guys. So now, example number, let me change the color so that you will have little good flavor. Okay, 10.1023, example number, oops, 10.23. It says that now, guys, if you know how to find x bar. X bar is nothing but summation of xi. My I runs from 1 to 10 because I have 10 observations and divided by n, so divided by 10. If you add all these things, I did this work for you, so it is 10.06. You're going to find this one. You are given alpha equal to 0.01, that is given to you. That sounds good, but you are not given your sample variance. So I would like to find S square. Now S square can be obtained using your chapter 8. So this is your S square is equal to, what was the formula? Summation, if I'm not wrong, I think it was xi minus x bar. So whatever x bar you got it over here, use that x bar over here. And xi is your x1, x2, x3, all your 10 observations. And whole square and divided by n minus 1. This is by, I think, chapter 8. Yes, if I'm not wrong. And that is equal to, if you use this one, you're going to get your S square. So your S with square root number, you're going to get that is equal to 0.246, right? You need to calculate all these things, guys. Yes, sometimes it is a little bit time consuming too. So please be careful. One more thing. My H0 is nothing but H0 is nu is equal to 10, and my H1 is nothing but nu is not equal to 10. Because it is not equal to, that means you have the normally distributed curve. Here you have alpha by 2, and here you have alpha by 2, two-tailed problems. And two-tailed problem, that means whatever the alpha is given to you, 0.01, that alpha equal to 0.01. So alpha by 2 is equal to 0.01 divided by 2, so 0.005. 0.005. As I told you, that sigma is not given, so sigma unknown. Let me write here sigma unknown for this problem, sigma unknown. But we have that sample variance, right? So sigma unknown, that means we rely on table A3. So I'm going to write, first of all, I have to find my degree. I mean to say degree of freedom. So S is equal to this one, and what is my V? My V is nothing but V is equal to n minus 1, right? N minus 1. So N is equal to 10. So 10 minus 1, that is equal to 9. So 9 degree of freedom. It is degree of freedom is equal to 9. Right, guys? Degree of freedom, that is equal to 9. So T alpha by 2. So I'm going to find now T alpha by 2. That is equal to T 0.005. That is equal to something over here for V is equal to 9. And that you are going to get, because here you have your V and here you have some 9, number 9. And here it is, you have 0.005 on the second page of the table. And just match this number, you're going to get one value over here. And that value is nothing but negative 3.25. So negative 3.25. So once you have this negative 3.25, that means the critical region is, what is my critical number region? So something like this. This is negative 3.25 and here it is positive 3.25. So this is your critical region. This is your critical region. And here it is critical region. Critical region, that means you are allowed to reject your H0. But here you have to accept your H0. Okay, fine. So now let me find, I want to figure it out, right? Negative 3.25. Okay. Negative 3.25. Now let me compute. So compute T value. So T equal to x bar minus nu divided by S over square root of n. So if I plug this value over here, x bar is 10.06. I obtain minus my new value is equal to 10. Look at over here. My new value is equal to this really, really good example. New value is equal to 10 divided by 0.246. That is my S value, 0.246 through this one, right? 0.246 and divided by square root of 10. And if you use your calculator, you're going to get 0.77. And 0.70 is somewhere over here, 0.77 lies over here, 0.77. So do not reject H0, right? So your decision is do not reject H0. That is your decision, right? And write down the answer in terms of the real life problem. And now I would like to go for the last example, guys, because number of examples are there. I showed you the method also. Just follow the same method and try to solve the examples. And let me just save this file. Let me clear this window. And now I would like to go for, again, the book. So if I go for a book, I'm going to get which example we can go for either 10.26 or 20.27. Let's go for 10.27. Let's see here, because this is the example of two samplings and unknown variance, but I think it looks they are equal, but I have to make sure. Okay, let's read the example 10.27, and this is the last example of our syllabus of our course, and I would like to stop at that point. So let me go for this example. Rest of the things, please try to do it by your own, guys, and it's not difficult, but just try to do this thing. Let me help you out for this one. 10.27, last example. A study at the University of Colorado at Boulder shows that the running increases the percent resting metabolic rate. Resting metabolic rate, RMR, in older women. The average RMR of 30 elderly women runners was 34, higher than the average RMR of 30 sedentary elderly women, right? See, two groups. And the standard deviation were reported to be 10.5 and 10.2, two standard deviations. Standard deviations are reported. Okay, was there a significant increase in RMR of the women runners over the sedentary women? Assume the population to be approximately normally distributed and equal variances. Equal variance is given but unknown. Use p-value in your conclusions. P-value in your conclusions, right, guys? So read this example twice. Everything that is provided to us. Yes, my nu1 equal to nu2 and nu1 is greater than nu2, that is given to us, and we have to use some formula over here. Be careful, guys. 10.27, because you have two samples, unknown but equal variances. Unknown but equal variances, right, guys? Similar to example 10.6 in the illustration. Example 10.6, if I'm not wrong. 10.6 in the, where is it? Back. 10.6 in the illustration. Yes, guys. So please do that thing. Okay, so let me just close this book now and let me start this one. I hope you read this example 3-4 times by this time, and let me stop sharing this one. And finally, my last example. So last example with number 10.27. It says that, first of all, let me write it down for you. Unknown, but equal variances, right? And this is equivalent to illustration, what I say, 10.6, right? 10.6 in the book, in your book. Okay, guys. First of all, let me write my H0. So H0 nu1 equal to nu2, and H1 nu1 is here in this example greater than nu2, right? Example says, yes, standard deviation we reported this one. The average MI elderly women runners was higher. Okay, higher than the average. Okay, so it is nu1 is greater than nu2, higher. Good, guys. And nu1 minus nu2, that is equal to d0. But in this case, they are same, so equal. X1 bar minus X2 bar, that is equal to 34. Right? You are given N1 equal to N2 equal to 30 in the example. and you are given, now you need to find your SP. So, but you are given your S1, right? So S1 is equal to 10.5 and S2 is equal to 10.2. 10.2. So these are the given items. Given. Okay. 10.2. So I can find my SP. SP is equal to, you can write SP square or SP equal to square root of this one. So that is nothing but, you know, this thing that S1 square, I wrote it down, that formula again. Let me write it down. N1 minus 1 plus S2 square, N2 minus 2, and divided by N1 plus N2 minus 2. Divided by N1. Let me just make sure, guys, about the formula. Yes, I think I'm right. N1, yes. I was just a little bit not sure about this denominator, but it is under the square root sign because the whole square is there. Anyway, so now if you plug the values over here, you're going to get that is equal to, I don't want to say I calculated this one and no, I did not. Let me 20 S1 20 S, this is okay. Let me write it down for you. That is better. So that is equal to 10.5 square and 29 plus 10.2 square and 29, because N1 and N2 are same. 29, 30 plus 30 minus 2. So that is equal to 58. That is equal to 58, everything under the square root sign, and that is equal to 10.35. So that is my SP, 10.35. Okay, now I would like to go for my T distribution. So T is nothing but X1 bar minus X2 bar minus D0 divided by SP and square root of 1 over N1 plus 1 over N2. That is equal to X1 bar and X2 bar. That is nothing but 34.0, right? X1 bar and X2 bar, that is equal to 34.0. Okay, guys, 34.34 or 34.0 or 34 minus 0, you can say 34, and this is because new 1 and new 2, they are same. Okay, so minus 0 sounds good. And here it is 10.35, that is my SP, square root of 1 over 30 plus 1 over 30. And if you use your calculator, you're going to get that is equal to 12.72. That is equal to 12.72. This 12 point, oops. This is 12.72. And now I can find my T greater than 12.72, right, guys? Because we need to find the probability. Okay, confidence interval is not given to us because we did not provide significance level. So I can write now what? Probability or P value, you can say. P value, that is equal to probability of T greater than this T alpha. So that is equal to this one, 12.72, right? 12.72. So that is equal to 1 minus probability of T less than 12.72, table A4, that is almost same, almost 1. So that is equal to, most likely you're going to get 0. Hence, we conclude that the running increase, the mean MRI is in older women, right? So reject H0, reject H0, and hence the conclusion is that running INCR increases the mean RMR in OL, older women. And that is the answer. And I think this is the end of the course. Thank you so much. And hopefully see you at some other point of time. Thank you guys. Let me save this file and just try to take the advantage of all this hard work which I have been doing, which I did for you guys. Try to take the advantage and good luck to you. Thank you so much, guys. And yeah, let me save this one, stop sharing everything. Take care, guys. Good luck to your future, for your career.